We found a serious one. On the other side there is quantum gravity, but we don't have the key. There are places where photons can't escape, and what happens inside is a mystery today, but we are sure they exist. In our universe, we have two big theories that allow us to explain things. Gravity with Einstein, say, or Newton. And one that applies to what we call quantum physics. Well, black holes bring them together. It's these small things that string theory or loop quantum gravity tries to find.
And we have just reached an important milestone in our understanding of black holes.
Hawking's black hole era theory first predicted this from general relativity, and then he succeeded with a colleague in integrating it into a broader theory. It's the only equation we know that unites all known theories. That's some strong work.
Christian Galfard, you obviously know how to estimate the number of galaxies in the other universe.
Me, like this, there.
You know the estimate.
In the billions.
But you, how many times?
1,000 billion is the number of galaxies in our visible universe. Observable, yes. Observable. It doesn't mean there aren't any, in reality, many, many more. But the one we potentially have access to, that's it, more or less.
So, do you know how many times we've asked you to explain a black hole? Because it's a nice number. Because it's a nice number. Christophe Galfard, you are known as one of the French specialists in the origins of the universe, black holes. So this time, we'll ask.
Because it's a black hole. Imagine the sheet. Spacetime is a sheet. If you put a concentrated or large enough mass on the sheet, you will create a well. You can create a well so deep, with walls so steep, that you will never be able to get anything into that hole. You can never get out. Not even light, the fastest thing, which has no mass. So that's the idea of a black hole, meaning, are there in the universe areas where there is mass concentrated enough to have created this kind of tear in spacetime, or else a much larger mass, not necessarily very dense, a supermassive black hole, for example, millions or billions of solar masses. It's not necessarily very, very dense, but it's so heavy in a relatively restricted area that it will create this kind of, so we call them holes. Obviously, we don't know exactly what happens in a black hole, which is fascinating, but we just know that there are these places from which photons cannot escape, and what happens inside is a mystery today, and we are touching the frontiers of science, of what we can say about science today. And what is quite fascinating is that these black holes, which appear to be objects, I imagine, well, when Kerr made his prediction about the black hole and all, the idea still seems quite plausible, and knowing that we managed through observations to verify that these objects exist, which doesn't diminish their magic, there are still as many mysteries about black holes today, I think before, but on the other hand, we are certain they exist, and I find that wonderful.
Christophe Galfard, you validate.
On density, I can say a word. I like the tablecloth look. Often used, but it has a small drawback. It's like the black hole is flat. Oh yes, no, but it's a bit more like that. Since it's a bit like a round Earth, which will attract things in all. No matter which direction we fall, it will go in. And I like to see a black hole like a kind of ball, with an interior space extraordinarily larger than we think from the outside. As soon as we get in, it's like a magic pocket in the animal drawings where you can put a bike, a house, an airplane in a pocket. Marie Popin's bag. Marie Popin's bag where you can put absolutely everything. A black hole is similar. Except unlike Marie Popin's bags, you can't get things out of them, they don't come out. But in idea, that's it. Meaning there's a volume much larger than the surface suggests. And this volume is created by a mass collapsing in on itself and attracting the space around it, sucking in the space and pulling it in all directions. What happens is if we are too close, we will slide along this stretching space and be drawn to what is in the center. The overall density, it's not much. But the point itself, or the ball with that matter that collapses and gives birth to black holes, it can reach density so extreme that we don't know what happens there. The rest, far from this. Even if we pass the point of no return, we still have a small idea of what's happening. It's really the meaning, so it's not too much. Because we are at the limit of theoretical knowledge, and so, at the beginning of the theoretical research.
We have no idea. We don't have leads or suggestions.
Basically, to answer briefly, in our universe, we found two major theories that allow us to explain things. There is one that applies mainly to the very large, for gravity with Einstein, say, or Newton, and one that applies to the very small, which we call quantum physics. And the two don't work well together. They walk extraordinarily well, each in their own way. They allow us to predict. That is, before we look, with precision up to, after the 14 digits, after the comma. And that's it. When we check, we get the same results. So it's one of the theories with unmatched predictive power, but each in its own way. As soon as we try to put them together, we realize they don't have the same notion of space, the same notion of time, that there are strange things everywhere, so they don't communicate. We could, but we don't. There's one, the very small, the other, the very large. Let's keep them separate. Why is she bothering us to bring them together? Well, black holes unite them. So we know that in nature, there are huge objects that become tiny, black holes. Or the Big Bang itself. So, if we want to reach black holes, the center, strange places, or the Big Bang, we will really have to bring the two together. But we don't know how. There are theories, like the string theories everyone has heard of, or those Carlot Rovelli often talks about. Which is another way to unify gravity and quantum physics, called loop quantum gravity, which is very beautiful too. There are about 30 other theories trying to unify the very large and the very small, what is called quantum gravity, but we don't have a single one that is unanimously validated yet. They have trouble making predictions. String theory predicted supersymmetry of new particles that have never been discovered. So that's problematic. Gravity on its side tries to make astrophysical predictions about black holes by predicting white holes. The problem is we haven't seen the white hole yet.
The white hole that would be the exit of black holes?
Apparently the release. Black holes collapse matter. And what happens when it reaches a certain level of compactness where space is quantified and thus made of quanta? There's a point where we can no longer really compress matter, and at that moment there will be a rebound and the black hole would explode and thus return the quantum foam to its initial state. This phenomenon would be immediate for the black hole would, except it dilates time, so for us, it would take billions of years from the outside. So, the theorists make calculations that are not quite ad hoc, but almost. So they say, for us, that would take 10, 15 billion years. And since the universe is 13.8 billion years old, we're not far. We're not far, so maybe we could find holes but maybe the theory isn't right either. But after, we can laugh at many predictions or non-predictions of these theories, but it's a classic case when we reach the limits of knowledge. To guess what lies behind, it is the pure imagination of the researchers that will wander and try to find things to tell and ways to express them to make predictions. And it's not simple, because we are beyond knowledge. So generally, you have to invent language, mathematics, calculations, find the right things, and it takes longer than expected. It might be a shame for the impatient. But the road can be very long. Between Newton and Einstein, 180 years passed, linked to planets not orbiting the Sun as Newton predicted. One in particular, Mercury, to explain, 1,000 other things were highlighted. The one who was good in the end, Einstein's, who took a completely different direction from all the others. I like that you talk about imagination because it's something we forget a lot and that will return at the beginning. Science is much imagination. I remember when I was little, the image of the Earth, cut into quarters, showing the core, mantle, crust, and the day I realized we hadn't drilled more than, made a hole over 10 kilometers into the surface, but in fact, all that vision, its signal analysis and its imagination. Imagination draws it. It's seismology, so the study of seismic zones, but you still have to be able to visualize it. In astronomy, it's also true. There are many, even if there are very beautiful images that can help. Geology isn't the case, evolution theory is the same. We find fossils in an impossible state, in sedimentary layers. We have to admit making all this effort to rebuild the dinosaur world. Today we saw Jurassic Park, so dinosaurs seem, but the dinosaurs aren't good. Wrong colors, etc. But that was the dinosaur vision we had back then, in the 90s. But in the end, it doesn't. Over time, things change a bit, but there's still that effort of imagination. In theory, the step to take is even bigger. Because at first, we have no idea. It's beyond our senses. It's beyond what we access in experimentation. It's beyond everything. So, it's a bit like becoming a painter. While they had to invent the brushes, the canvas, and color, and gouache. Gouache, the material, to paint. We have nothing. So, some paint, and it's nonsense. And there are sometimes, accumulating all these attempts. Someone who sees something else, saying, "Wow, I saw it." And we arrived at a new vision of our universe. And it's quite nice. And then, we are in the period where, if one of the existing theories is correct, we just don't know it yet. If so, it will be a mix of all these theories for black holes, for the origin of life, for the Big Bang. That said, some can be lab-tested. For example, the origin of life, probably. The others are more complex.
Christophe Galfard, you're a physicist, a black hole specialist. You publish La Vie à Portée de Main at Albin Michel. So, we are very happy to have you now, because Tristan, we've had a small upheaval in your field of expertise these past few days. We've just reached an important milestone in our understanding of black holes. Tristan.
In any case, it's a very nice experimental observation. Have you heard of gravitational waves, first observed 10 years ago, which was an Einstein prediction, and occur when very dense objects spin very close to each other? They will dissipate energy around them in the form of gravitational waves, a type of spacetime vibration that will spread through space at the speed of light and reach us, passing through the Earth. These are truly tiny variations, but we can measure them with very high-quality lasers that cover several kilometers. We detected these small vibrations and observed a black hole merger, which associates individuals that happen not too far from us, with instruments that have been updated and are a bit more sensitive than before. And these two black holes merged, they emitted a gravitational signal, and we managed to measure the parameters of the resulting black hole with unprecedented accuracy. So we managed to confirm one of Stephen Hawking's predictions, who was a British official, who recently died, famous among all, who had ALS, Charcot's disease, whose silhouette in his wheelchair is known to everyone. He made a prediction in his youth in 1971. He said that in two merged black holes, the resulting black hole should have a larger area than the sum of the areas of the two initial black holes. What's not trivial is that some mass is lost, so there must be compensation. And we could never verify this prediction. In 2021, we still lacked some precision. Gravitational zones already allowed observing some of this. So, that was announced last week, for the 10 years, this signal, which verifies this theorem, what we called Hawking's black hole era theorem. So it's a very nice experimental proof, and we don't often have experimental validation for theories of this nature. The discovery of gravitational gifts in itself won a Nobel, because it was a prediction, so not Einstein directly, but even if. he finally subscribed. 2 Nobel Prizes. But 2 Nobel Prizes. And there you go. So, I don't think that would have earned Stephen Hawking a Nobel Prize. The question can be debated. Because these predictions he made, Hawking radiation, black hole evaporation, are beyond the reach of telescopes today. He should have won the Nobel Prize with Penrose shortly after his death, the year after his death. Which probably means, if he hadn't died in 2018 but had waited a year or two, he would have won the Nobel Prize during his lifetime for all his work on black holes as pink sentences. That is quite probable. But regarding this detection, there's something funny. How do we see this? How do we detect in a vibration that moves lasers, things that happened hundreds of millions of years ago, and say the initial black hole was this size, this one that size, and the resulting one is this size, when they are objects we aren't supposed to be able to see, since very little comes out of them? The definition of gravitational waves you're talking about is exactly this: they are hyperdense objects that create waves in spacetime. Well, now it turns out that when we disturb a black hole, there are calculations, notably by a Frenchman named Typo d'Amour, that show black holes will vibrate a little when they are entered or when something happens to them. And those vibrations will impact the waves that go out. They're called quasi-normal modes, sort of. And based on the shape of these waves, thanks to the work of Hawking and others, we can determine the size of the black hole and its initial mass. And it is precisely by seeing these tiny vibrations that last for an infinitesimal time that we can detect them in non-gravitational detectors. We can say it was the mass of the initial black holes and thus the size of their surface. That's some serious work.
Tristan, you also told me about this equation, but I'll let you speak because this one is beyond me.
So nothing related, it's just that Hawking's black hole air theory, he first made this prediction starting from general relativity, by many calculations. And then, he succeeded with a colleague in integrating it into a broader theory. That is, he calculated the entropy of a black hole, saying it was proportional to its area. So entropy is the measure of disorder. It's a notion that's a bit hard to grasp. Even for physicists, not all girls agree on how to interpret entropy. But so, what we see in Tenet.
I find this one of the clearest descriptions of entropy. It shows how complicated it is.
And there's a law of thermodynamics stating entropy always increases. So, if a black hole's entropy is proportional to its area, it means its area can only increase. Finally, we say the same thing in 2 ways. And this equation on the entropy of a black hole involves all the constants of physics, notably constants from quantum mechanics and constants from general relativity in one equation. And it's something quite. It doesn't mean we found a unifying theory for quantum mechanics and general relativity, but we managed to make them coexist in the same universe. And I find it quite fascinating, this equation that can be expressed in entropy or temperature. There is a very close link between temperature and entropy. This led to this question, which was very simple to see. But actually, it's simple. It's not a complex question. I can put a small caveat on the question of what entropy is. Because in reality, we yield when talking entropy. Afterward, there can be several different definitions, but every time we have a definition, if we take that definition, then we know exactly where we are starting from. It's not that mysterious. No, mathematically no, but how is entropy? For a black hole, there's something special. If you look at a black hole from the outside, by principle, from the object, there is a limit distance from which nothing can escape. Every time you mention surface, air, etc., we're talking about that surface. It's the limit, the point of no return, that won't move much no matter what happens inside. It will stay there, it will give us a black sphere surface somewhere. Where is the place from which no light can escape? This surface, what Hawking and his colleagues discovered at the time, is intimately linked to what happens inside or what happens on the surface itself, even though there is nothing. And intimately, its equation tells us that this surface will depend a little on all the things we could store on the surface. And that becomes amazing because we have a surface that contains nothing, yet stores things. And everything inside the black hole should have an image on this surface. That's what the anthropic principle means. We store something with volume at a black hole surface. And that is extremely surprising. In a way, there are possibilities inside black holes that will manifest as a temperature. You can't have anthropics without a temperature to play with. What makes black holes suddenly become thermodynamic objects? Everything I just told you may seem complicated. But what does thermodynamics mean? Thermodynamics is the temperature around us, the things around us. These are concepts that don't exist in themselves. These are concepts that appear when there are many particles. For example, the temperature we feel on our skin is the average speed of things hitting our skin. That's what you call temperature. If you have only one particle, the concept of temperature doesn't exist. There must be lots. I give another example, a grain of sand. Sand has meaning. The concept of a sand dune doesn't exist with one grain. You need lots of them. The fact that black holes are thermodynamic objects means they are made of many small things. It's these little things, we don't know what they are. It's these small things that string theory or loop quantum gravity tries to find. And as we said earlier, black holes themselves bring these small things, the tiny and the very large, together through gravity. The fact that these are thermodynamic objects tells us they have a temperature, and this temperature is the equation you mentioned earlier, which has the particularity that it is the only equation known in all scientific disciplines that unites, as you said, all known theories.
Can we describe it, since I can't see it?
There's the little h that tells us there's quantum physics. C is the speed of light, so it's very fast. K is the Boltzmann constant, meaning there are statistics in it. And G is Newton's or Einstein's gravity. So this equation, what it tells us, and you didn't say it, but I'm sure we agree. For me, in any case, it's the most beautiful equation in theoretical mystery today because what it tells us is that a theory of quantum gravity exists, and whatever it is, it will have to find that result. Basically, this is a serious hole, we found a serious one. On the other side, there's quantum gravity, but we don't have the key. We just see through the series that there is this equation, and we don't have the key to open the inside of a black hole or the Big Bang.
It is as beautiful as frustrating, that equation.
That's great.
There, with black holes, is a world-like, universe-like side. Can we one day imagine a universe entirely swallowed by a giant, ultramassive black hole that would absorb the entire universe? Is that part of possible theories for the end of our universe?
So, what this equation we talked about says, the temperature of black holes, entropy, etc., it says that black holes are not eternal, that they re-emit in the form of radiation, maybe other things, we don't know much about what fell inside. So, even if a giant black hole engulfed everything, it would re-emit things, so it can't swallow everything. We cannot have a whole global reality swallowed by a black hole. Part of reality, yes, but as this equation says, it will always come out.
Thanks, Christophe Galfard. I remind you of the release of your book Life Brought Tomorrow, and also the previous one. It was The Universe Brought Tomorrow, where you talk about the black hole issue. Thanks, Tristan Regs. We inform scientists at Figaro. See you soon for the next planetarium.
We don't feel like moving. Not bad.
Not bad.
Not bad.